Hi everyone, hope you guys are doing well. So here's the part 3 of our chapter 7. Okay, so we're going to start with wave particle duality of matter and energy. Everybody is so familiar with this equation E equals mc squared, right? So this has a matter and energy as alternate forms of the same energy. Here E is our energy and m represent the mass, and then c is the speed of light. Okay, what happened now? Go back. Okay, right here. So you can see all matter exhibits properties of both particles and waves. Electrons have wave-like motion and therefore have only certain allowable frequencies and energies. Remember, we learned about that the waves that we get from the electromagnetic radiation, they have frequencies, they have wavelengths, they have energies. So electrons are also considered as waves. So electrons also would have frequencies, energies, and wavelengths. Matter behaves as though it moves in a wave. So the scientist named de Broglie, he came up with an equation that if you want, you can find out wavelength of any particle by the equation given below. You see, wavelength equals Planck constant over mass times u. U is the speed in meters per second. And these are some de Broglie wavelengths. You can see comparing to a slow electron, also to a huge mass of Earth. All of these has a certain speed and also they all have a certain wavelength. So wave-particle duality. So what is this wave-particle duality? So we all can read this together. Classical experiments had shown matter to be particle-like and energy to be wave-like. That's what comes to our mind whenever we think about a particle. We think that's a matter, and then if it is energy, energy to be wave-like. But results on the atomic scale show electrons moving in waves and photons having momentum. Thus, every property of matter was also a property of energy. The truth is that both matter and energy show both behaviors. Each possesses both phases. In some experiments, we observe one phase. In another experiment, we observe the other phase. Our everyday distinction between matter and energy is meaningful in the macroscopic world, but not in the atomic world. The distinction is in our minds and the limited definitions we have created, not inherent in nature. This dual character of matter and energy is known as the wave-particle duality, meaning particles have wave-like properties and energy has particle-like properties. So the next figure that we're going to look at, going to summarize the theories and observations that led to this new understanding. So classical theory considered matter to be particulate and massive, energy to be continuous and wave-like. Since matter is discontinuous and particulate, perhaps energy is discontinuous and particulate. Okay, so there were observations done and we have seen black body radiation. Anybody remember what is black body radiation? That is emitting light when you heat an object to a very high temperature, right? So we were able to see a color, meaning the wavelength and energy are interrelated, right? So that was done by Planck. Energy is quantized, only certain values allowed. And we also had seen photoelectric effect, and that is when a photon of light hit a metal surface, it ejects an electron, and the ejected electron can go through an electrode and produce a current. So that is called the photoelectric effect. That was found by Einstein. So that tells us light has particulate behavior, which is the photons. And then the scientist Neil Bohr, he talked about atomic line spectra. Remember how he deduced the hydrogen atom structure using those atomic line spectra? That tells us energy of atoms is quantized. Photon is emitted when electron change orbit. So since energy is wave-like, perhaps matter is wave-like. So likewise, there were so many other experiments were done, and then it came to the quantum theory, which is energy and matter, particulate, massive, and wave-like. Over here. Okay. So if you have a wave moving, Heisenberg uncertain principle states it's not possible to know both the position and momentum of a moving particle at the same time. Okay, if you have something moving like that, so you want to find out the position. If you want to find out the position accurately, then it has to stop moving. And at the same time, if you want to find out the momentum of a moving particle, it has to keep moving. Right? We can find only one thing certainly or accurately, meaning more accurately we know the speed, the less accurately we know the position, and vice versa. So the Heisenberg uncertainty principle is it's not possible to know both the position and momentum of a moving particle at the same time. Go back. Oh, come on. What's happening now?